Okay, for our next talk, Lee is going to talk about recent progress on Euclidean and related spanners.
Right, so my original title is about only Euclidean spanner, and then, which back then when I submitted the talk abstract, but when I made the slides, it feels difficult to ignore other. Not just Euclidean, That's the thing. The second thing I want to say is that there's no technical detail in the talk, so the talk would be very different from other talks in the program. I'm not sure it's a good thing, but it's just a different thing. Okay, so we hear about Euclidean spanner in a couple of earlier talk in this program. So hopefully I don't need to spend a lot of time. So what is a T-spanner? So first I'll give you the definition in matrix spanner, meaning that you're given a matrix spaces, you give a set of points in the matrix spaces, and you want to construct a sparse subgraph that almost preserve distances between every pair point up to a factor of T. Okay, and the weights on the edges of the spanner are gonna be the distances between the 2 points in the space. Okay, and also when we talk about spanners, there are two criteria that we're looking for. The first is that the spanner has to be sparse. If let's suppose that you figure step, let's say 2 or maybe 3.5 here, and then you want a sparse spanner, and this measured by sparsity, which is the number of edges of the spanner that you have over the number of points, or the number of edges of any spanning tree. But the reason I put MST is because of the linus, which is you want the spanner. Sometimes you want the spanner to have a total edge weight to be small, and the smallest you could get is a minimum spanning tree, because at least you have to connect everything together. And so we want to compare how much more you want to pay compared to MST. So that gives the definition of linus, which is the total edge weight of the spanner over the weight of the MST. So even for sparsity or linus, you want to be competitive with a minimum spanning tree, because it's a sort of like simplest connected graph that connect everything. And this is going to be a function of this stretch. So graph spanner is very similar, but you given a graph, and then you just want to edge weighted, and you want a spanning subgraph that preserve every distances. So think about matrix spanner is you start with a complete graph with weight on going to be distance between every pair point, and graph spanner is the graph might not be complete. Okay, and also have notion of sparsity and linus applied here. You want to be competitive with the minimum spanning tree. And another, typically, Euclidean metric, I probably don't have to introduce, but something called doubling metric, but I don't know whether people know about doubling metric. And how many of you know doubling metric? A few. Robbie definitely is the person who introduced this notion. So, all right, so what is doubling metric here? So doubling metric is a metric where if you look at any ball of radius r for any r, you can cover it by 2 to the power of d ball of radius r half. So if you can do this for every ball, then you can say that the metric have doubling dimension d. Okay. And doubling dimension sometimes it's good to think about as a discrete version of Euclidean metric, because Euclidean metric have doubling dimension d, plus some very small constant. And so one interesting thing is that any metric space you could have a doubling dimension at most order log n, because you can cover every ball radius r by n ball radius r. But it's not the case that any metric can be embedded into Euclidean metric of dimension log n. So somehow the doubling metric is sandwiched between Euclidean and general metric. Okay, so spanner been studied, Euclidean spanner been studied decades ago, starting from a paper in '98, where probably the first, as far as I know, construct a spanner with constant stretch and with only linear number of edges, or maybe constant sparsity for points set on the Euclidean plane. And then a massive amount of work afterward trying to get the stretch out to 1 plus epsilon for any fixed epsilon, and also want to extend to higher dimension. I'm going to miss a lot of references here because, we start from 90 something up to now. So it's a lot of work. The nice thing is that if you want to look for more references, a whole book about it, okay? Which is basically, for sparsity, you can get 1 over epsilon to the d minus 1, where the order d high, some exponential depending density on d. Let's assume that the dimension is low now. And then the Linus is a little bit off by a factor of d, by a factor of 1 over epsilon. So Linus, you can get something 1 over epsilon to the power of d. Here is like sparsity d minus 1. So it's off by a factor 1 over epsilon, and it's not necessary. So these bounds are tight. Understand Linus is much more difficult, so we just settled it very recently. But sparsity is very well understood. The whole book about this thing. For doubling metric, you can get sort of similar result. Sparsity 1 over epsilon to the power of d, and then Linus is also off by another 1 over epsilon factor. And these are sort of the offset between sparsity and Linus seem to be necessary. So, these are very basic results. And some observation is that, if you want to forget about every number, then, a good thing to keep in mind that you can get that 1 plus epsilon. Sparsity in Linus is off by 1 over by a factor of 1 over epsilon, which is tight. And doubling is off by 1 over epsilon factor compared to Euclidean. And the reason is Euclidean geometry, where you can have notion of angles and things like that. So these are basic results that we know for a long time. In graph spanner, we also have a set of basic results that we know very well. For example, you can get 2k minus 1 spanner with sparsity n to 1 over k. So think about 3 spanner, then you get sparsity square root n. 5 spanner, you get something like n to 1/3, something like that. And this is tied under the Eddy-Schurz conjecture. So it's also very well studied. But Lie spanner is more difficult. You can see the research is up until now. People are starting to. And the thing is that for Lie spanner, you can get 2k minus 1. Now somehow there is 1 plus epsilon here. And then with Linus, there's still 1 over epsilon off. Even in both the geometric setting and general graph setting, there's also sparsity in Linus somehow off by 1 over epsilon. And the stress is 2k minus 1 plus epsilon Linus. And so for a long time, I believe that there shouldn't be that epsilon here. But now I changed my mind because there was a paper since, a couple of probably 1-2 months ago or something like that, where with Baldwin and Flick, they show that it's probably necessary for a very specific value of epsilon, not for the most interesting thing is when epsilon probably about like 1 over square root k, whether it's necessary, it's still unknown, but it seemed like necessary. And here's the Eddy-Schurz conjecture, just in case you are curious. So these are basic results. And there is one simple algorithm that produce all kinds of results that I show you. Okay, a single algorithm that gives good spanner in every setting that I told you, which is kind of weird. It's called greedy algorithm, very similar to classical. You just short the edges in the increasing order of weight. And then when you up to consider an SUV, and then you want to see if the distance between two endpoints of the edge is currently too large compared to the weight of the edge, then you put it to the spanner, because this edge seems to be necessary. It currently is. So, and otherwise, if the distance between all in the spanner is already good, then you can ignore the edge and consider the neck. Very similar to classical, it actually all the aforementioned bound in all settings. Okay, this is kind of weird. And this can be explained by the paper by Fusel and Sullivan, where they show that greedy's algorithm existentially optimal. I wouldn't go into the detail of what it means to be existentially optimal here, but there are also some work trying to explain why greedy is so successful in all settings. Okay, so these are the basic results. Okay, so any questions? So these are kind of results that people know a long time. Now, my favorite is fault tolerance, and what up with fault tolerant? So basically, the idea is that we want to construct a spanner so that it remains a spanner after you remove a certain number of edges or vertices, right? You can think about a network where the vertices might fail, right? And that they not be functioning anymore. And then you want to build a spanner so that even these point or edges fail, you still have a good spanner afterward. Okay. So matrix spanner is F fault vertex tolerant. If for any set of points that are at mode F, then the remaining is still a T spanner for the remaining point. Okay. And the graph fault tolerant spanner is defined more or less the same. So these are the vertex definition, but you can apply to edges notion of fault as well. And this is actually the fault tolerant spanner as a definition is coming from Euclidean, and then people study graph. So what do we know? So we know that, at least in the constant epsilon and d case for matrix spanner, you need at least, order f times n number of edges, because every vertex had to be incident to more than at least f vertices. Because if all the neighbors fail, you don't want to disconnect the point with the rest. Right? So sparsity is order f, and line have to be order omega f squared by Schumann and Zhao. And then we also, achieve basically the same, upper bound matching the lower bound. Okay, so this is what we know, even for both the vertex version and the edge version. And these results are extensible to, low-dimensional matrix spaces as well. Okay, but the graph spanner is, fault-tolerant graph spanner is also, I would say, very interesting, which is, all these lower bounds conditioned on the Eddy-Schurz conjecture, and then with the same conjecture, you can extend some sort of, assuming the Eddy-Schurz conjecture, you can also extend to get, lower bound on sparsity and lightness for F vertex fault. So this is a metric like, doubling metric and Euclidean metric. But the graph version, then you have some sort of like, some dependency on F here in the lower bound. And then, there are sequence of work starting from the paper in 2010. There's some work by Virginia as well, where you can get exactly these matching upper bound, more or less. So that's what we know, but we don't, at least I'm not aware of a light version where, maybe the light is trickier because whether you want to be competitive with a minimum spanning tree or not. Even the definition of light is not that immediate because the minimum spanning tree is not fault tolerant. So, but at least I'm not aware of. Okay, so, the question is, can you get some light? But also recently, I'm more interested in the massive failure regime, where the number of faults could be linear on the number of vertices or edges. So that is interesting. I'm interested in this massive failure because it even clear how you define what it means to be a good model of fault. You can't just say, okay, F vertices fail with N vertices fail, then in all these other, in the classical definition of F fault tolerant, you need N squared, and it's not giving you anything interesting. So for massive failure, the fault model is very important. Okay, so one model that I'm interested in is reliable. Reliable here just means the following. Let's say that you had, and the number of fault right now could be up to like linear, like half the number of vertices. It could be massive. Suppose that you had some set of vertices that are faulty, and then in this model, you are allowed to extend the faulty sets to be F plus here, including all the faulty, and then some other point. But the restriction is that these F plus here have to be small, relatively small compared to F. And what kind of guarantee do you want? You want the guarantee that for every point that are not in this, F plus here. So you only need to preserve distances for points that are outside F plus. Meaning that, okay, so X and Y here, you have to preserve distance. But if X here, for example, is not faulty, but in F plus, then you don't have to preserve distances for the points that are in F plus. Okay, even though they are non-faulty, but you're not required to. So basically, you can think of F as faulty point and F plus a dangerous point. But dangerous point, you don't have to preserve distances. Only have to preserve distances from the safety zone, where the point. And for the safety zone, you are allowed to use vertices, dangerous vertex, but you are not allowed to use faulty vertex because they are faults, so you wouldn't be able to use this. So this is a interesting model, and you can get something. But remark that this model doesn't work for graph. So we show that you apply this definition to graph. The best you can do is then square, like the lower bound. So really, you have to be very careful with the model of fault. And in this model, in Euclidean, you can get sort of like lower bound. You know that the sparsity can't be constant, so it has to be omega log n. And then you can get upper bound that are sort of like more or less matching the lower bound. So these have worked very well for the metric version, but somehow it doesn't work for graph. The model of fault is very interesting. And then also you can ask the question of lie and spar, and that is all about lie and spar as well. And another model of fault, so the reliable spanner that I told you, where in this model the edges, the point are faulty. But here there's another model where the edges are faulty. It's sort of like the edge counterpart of reliable. It's a very new paper where after you build a spanner, some of the edges could fail with a certain probability. So, but I wouldn't go too deep into that. It's just saying that there is an edge counterpart version of this thing. So in graph, there is, I think, a very interesting model of fault, which is the color model, where basically the vertices and edges are partitioned into color classes. Okay, it could be more than F color classes. It could be many color classes. And one color class could contain so many vertices. But in these models, at most F color classes fail. Okay, one color class could contain so many vertices. But as long as you have at most F color class fail, you can still say something. You can still do something non-trivial. So basically, you can get sparsity of F times n to the 1 over k. So really similar to this classical spanner, but you can pay more in terms of F, which is the number of classes that they fail. And really, in this model, up to linear number of vertices or edges could fail, depending on how many vertices and color class. So I think this is very interesting. It's also surprising that they can tolerate so many faults.
So technically, you only had like 2 colors for the whole graph, and 1 color is most of the vertices. Then wouldn't this reduce to the normal massive failure?
No. So you could have here. You could have so many color classes. You don't know. Let's say that you could have square root n color classes where a class contains square root n point, and at most F of them could fail.
Yeah, but you could have an instance where
if you have 2 and then 2 fail, then nothing to.
Two and 1 fails, and that 1 dominates most of the vertices. But then, isn't it going to be the same case as last time, where you had so many of your vertices fail? Just.
But then,
I'm asking if the colors that fail happen to cover most of the vertices, wouldn't that be the same as a normal massive failure fault tolerance?
It's a good point. It's not really the same because here the color class are fixed, okay? But in the mu reliable, you don't know which one failed. Right? You really don't know the faulty set.
Okay. Yeah.
Right. But here, when you know the color class, you can guess which part could fail, and then this is that's the difference. And then another model called bounded degree model, where this is only applied to edges, fault, or the edges, but where up to linear could fall, but the number of fault incident to a vertex is at most F. So in this model, you can also get non-trivial bound. This is applied to both metric and graph setting, where you can get really almost optimal bound in terms of the sparsities and lightness. Okay, so there's a different kind of fault model, but in this regime, we have to be really careful with the fault model. So obviously the gap between the Euclidean and doubling here of F here, you made a question: can you close this? The live version of these things. I haven't seen it, and I'm interested in hearing other model of massive failure. Coming up with the right model is tricky, and also when you had typically for massive failure, you need to bring interesting techniques to be able to deal with this. So I think there are really good motivation for coming up with other model of fault where it allows massive failure. So this is fault tolerant. Any questions? So another aspect of spanners that I really like is approximations, which is, so far I'm saying something like n to the 1 over k is tied under a discrete conjecture, or epsilon 1 over epsilon to the power of d is tied under certain adversarial point set, bad point set, let's say. But another sort of like more orthogonal is that let's say that you are given the input and you want to find the spanners that are as good as the best you can find. Right. So it's more like approximation question or instant optimal question where really you want to find the best spanners that are as far as the best that you could see in there. So there's a lot of work on approximating graph spanner, but it's good. But at least we can notice a good thing is that you can get n order n to the 1 over k approximation just based on the classical result, and you want to improve upon it. Okay, for example, when you had t equals to 3, meaning that k equal to 1, then you get square root n approximations for 3 spanner, and when you get 5 spanner, then you can get n to the 1/3 approximation. So these are something that you can observe from the greedy algorithm, and that could be the benchmark that we want to compare to be comparative with it. So there's a lot of work. Whether I would say a lot of work is, but there's a long line work from '94 here. For 2 spanner, you can get log n approximation. For 3 and 4 spanner, you can get n to the 1/4, which is better than this number you see here. Yeah, and for every constant t, I should say that t is at least 3. Okay, well, for every t at least 3 in any epsilon, you won't be able to hope for polylog. Okay, so something like it has to be polynomial in n. When it's just at least 3, I forget to include it. So it's a very difficult problem. Okay, probably not surprisingly. So, but the question is still, can you design a good problem algorithm with even polynomial but small polynomial approximation? It's not ruled out by the Lowell. And we only have n to the 1/4 for only 3 and 4. This is okay, but matrix spanner is somehow different. Also, I remember, when we look into this, a few hardness results saying that computing the optimal spanner is NP hard, but I wasn't aware of a good approximation algorithm, at least before I tried to work on this. And you had the approximation factor of 1 over epsilon to the d minus 1 from, let's say, the isothermal bound. Now, so maybe if you think about epsilon and d as constant, sure, then you get constant approximation, right? What else to be done there? But here I think about, there's something we're looking at is d not a constant and epsilon is not a constant. Then things will start getting interesting, but I'm not aware of any significant algorithmic result. So recently, that we design, 1 plus bicriteria where we design 1 plus order of epsilon, meaning there's some constant, absolute constant times epsilon, where our spanner is guaranteed to be log of d over epsilon as the optimal, where optimal is either the number of edges or the total weight. Okay, so this is bicriteria, and the dimension is a log. So it's like even applied to like linear dimensions or super high dimension, you still get log. So this is the thing that we did recently, and you can see there's a lot of interesting questions that you can ask. For example, could you get rid of the bicriteria, like the order of 1 over epsilon? Could you just remove the approximation on these in the stretch? And so how about t spanner for constant t, like say 3 or 4? Right? For 2, you can get log n, right, from the result for general metric. But how about 2, about 3 and 4? Could you get something like that? For general metric and graph, you wouldn't be able to do that because of some Hanit result, but there's nothing, prevent you from getting polylog for high-dimensional Euclidean point set. And so, and we only be able to get this result for Euclidean metric. We had no idea how to get it for doubling metric. So really, somehow Euclidean geometry is extremely helpful here, but just low-dimensional metric doesn't seem to enough to our technique wouldn't be able to wouldn't work without Euclidean geometry. So, this is, and the last thing that I want to say is, I have less than 5 minutes, but we'll see, a structural alternative. So what is structural alternative? You can think of spanner is a sparse subgraph, so there's preserved distances. But all it says is a sparse subgraph. It's more like compression. Now, sometimes you want to do, okay, I want to have the spanner, and then I want to do something with it. And then once you only have sparse subgraph, they only limit the thing that you can do with it. Right? So when I say structural alternative, I want a more well-structured kind of like data structure, so that it's, if you want to take spanner, that take, you can easily recover spanner from this structure. But this structure allows you to do more things. For example, one of these is called tree cover. So what is a tree cover? A tree cover is a collection of trees that you build on top of the point set, or even the graph. Okay. Where for every pair point, then there's gonna be some tree in the tree cover. I don't know which one, but there exists. I guarantee you that there could be exist one. But the distance in the tree, I got it wrong here. I should say dt here, and then dx here. But the distance in the tree is approximately up to a factor of t, the distance, the original distance in the metric. Okay, so basically, if I look at all the tree, then one of the tree going to preserve the distance for the 2 point. And this is guaranteed for any pair point. So they're going to be, I build a collection of tree where some tree going to preserve distance for, for any given point, for any pair. So for example, you look at this X and Y here, maybe this tree going to preserve their distance. The other tree might not. But, as long as I had one tree preserve the distances, I'm happy. And I want to minimize the number of trees. And so if you take the union of these trees, you get a spanner. So in some sense, but it's more structural because a bunch of trees, for example, it will allow you to do things like, if you want to, for example, query distances between 2 points X and Y, right? You can go through X of the tree here, and then compute the distance on X of the tree, and then return the minimum that you see. And computing distances, point tree is a very simple thing. So that allows you to build another structure like distance oracles and things like that. So it's more or less still trying to do spanner, but a more structural sense. So what do we know? Well, in Euclidean space, actually there isn't a lot of work. But right now we're able to bring the number of tree to be 1 over epsilon to d minus 1. But actually the notion of tree, so also in doubling metric, you can do more or less the same, but you opt by 1 over epsilon factor. But these are the tree. The tree here, I was just saying like the tree is only guaranteed to preserve distances, but nothing can, but nothing else about the tree that, the tree could be, the tree is obviously sparse, right? Because a tree can only contain few edges. But the one interesting open question is, do light tree cover exist? Meaning that the tree should look similar to the minimum spanning tree. Okay, could you build a tree cover where every tree look more or less similar to minimum spanning tree? That I think is interesting. Then you are way more constrained than you could, because every tree now had to look more or less similar to MST. There were some results saying that you can do log n, but log n is kind of like, it's not trivial, but it's something that you can infer from standard construction. Or maybe I shouldn't say that. For general graph, you can do with 2k minus 1 tree cover with this number of trees, and but I think Matar and Fandina and Neyman, they ask a really interesting question, which is, now suppose that you don't have so many trees. Let's say that you can only have 2 trees, or say you have 3 trees. What kind of stretch guarantee that you could get? So for 2 trees, they are able to get square root n, and for 3 trees, you get something like n over 1/3, and then more tree, the these stress reduce, but the no about. Okay. So, and the Eddy-Schwartz conjecture doesn't apply here, because Eddy-Schwartz conjecture is only about very small stretch. But the stretch here could depend on n here, square root n. So in their paper, they have some lower bound for Ramsey version of these. But for Valina version, I'm not aware of any lower bound. So, the question is, what are the lower bound? For 2, 3, can you get less than square root n, something like that? So I think this is a very interesting question. Now, if you want more structure, let's say that if instead of 3, if I want path, I probably run out of time. I don't know whether I should take another 5 minutes if you don't mind. If I want path, let's say that I want every tree in the collection to be a path. Would I be able to achieve that? Well, impossible, right? Because let's say that you had point set here where h and y are very far, and then all the other points either close to x or close to y. If you project into a path, then if you look at 2 extreme points, their distortion is going to be always big, right? Why? Because if you want to go from this to this here, that what it means in the real metric is that you have to go to all these points here, and then go to y, and then go to other point back to a. If you have so many points that near to x and so many points that near to y, you wouldn't be able to do that with few paths. Okay? You would still be able to do it maybe with n path, but not constant number of paths. And so you wouldn't be able to have this kind of distance guarantee. But then you can see that if you think about it, you have a set of point here, you project here, then what you can observe is that between x and y, every point is either close to x within epsilon distance here, or is close to y with epsilon distance. And if you want to guarantee this, you can make a definition called locality sensitive ordering. Where what is locality sensitive ordering? It's just a bunch of paths, so that for every point x and y, there exists a path q in this collection, so that every point between x and y in this path is either close to x or either close to y. So this is sort of like the guarantee that you could get if you really want path. Okay, you won't be able to preserve distances. And you can show that for low dimensional matrix, Euclidean doubling, you can build this only few paths with this kind of guarantee. And if you union all the paths, you still get the spanner. Okay, so it's still more or less structural alternative, but now it's a bunch of paths. But the amazing thing about this is that a path, this structural path, allow you to do so many things. You should check out the paper by Chan, Harper, and John, where they give so many other applications of this collection of paths, not just spanner. And here I give you another one sort of application. For example, let's say that you want to build data structure for querying nearest neighbor, approximate nearest neighbor. What do you do? If you have this collection of paths, all you do is take a point, look at the 2 neighbors in the path, right? For each path, you have 2 neighbors. And you go through all the neighbors in the set of paths and just pick closest one. And the number of neighbors versus the number of paths, basically. And that gives you very fast query time if you can construct this thing. And not just locality sensitive ordering, not just approximate nearest neighbor. You can build so many things beyond this collection of paths. And that is what the power of this data structure. So open question is, what could be the other structural alternative to spanner? So it's not just like spanner, but some structural alternative is useful for other different kind of problem as well. And for that, I want to conclude my talk. There's a lot of things that I didn't touch upon. For example, spanner in high dimension, spanner in different model computation, dynamics or MPCs, or some Ramsey tree covers. These are, but there's a lot that I wouldn't be able to cover in this talk. And I already over time, so thank you.
Questions, Bob? Is there a fault tolerant where model where you can have weights added to edges, so the adversary has a budget,
right?
And they can use that budget to delete vertices, but every vertex also has a weight. So like one vertex could have a weight of 1, the other has a weight of 10. So to delete the 10, instead of deleting the vertex with 10 weight, you can delete 10 small vertices with weight. Right. Is there some?
Not that I'm aware.
Could you just go back to the 2-tree question? I don't have a question. I just want to take a picture. Thank you.
And can you show the approximation for graphs, like the page with all the approximation ratios for the graphs?
Approximation ratio for graph. Okay, so okay, good. First, I'm not the authority on this sort of thing, so maybe I miss many citation here, but at least this is what I could find.
And that's good enough for me.
So in your final slide, the things you didn't talk about, you mentioned like spanners and various models of computation. Are there any specific?
For example, dynamics. Right. So dynamic, or some people explore MPC, which I'm not quite familiar with. But dynamics is really interesting. Can you have dynamic even with graph and
Also, you mentioned applications for path covers, like the tree covers. Did you mention that?
tree cover, I was just saying that you can do, for example, you can use this Distant oracle.
I see. Okay, right.
So when query distributed, you can go to each of the tree and you query it.
Yeah, any other questions for him? Okay, well, thank you again.
Thank you.
So we have a break. Well, we have discussion time now.